Hello, welcome back. I will today try to summarize what we have learned in terms of the iron chemistry. Okay. Iron, as we have discussed at the very early stage, is one of the most abundant metal on earth, and it is no wonder biological system has taken up iron and therefore has utilized for doing various important chemistry, like these are the redox chemistry. These are going to be exciting chemistry where both the iron oxidation state as well as, for example, oxygen oxidation state will vary. We have seen first of all the oxygen transport by iron, right. We have seen in case of hemoglobin we have this iron 2+ high spin species which is outside the plane and bound with histidine. It is pushed in when iron 3 oxo species is formed, or iron 3 super oxo species is formed. This is the reason why we are alive, right. This is beautiful chemistry supported by these beautiful side chains, and this chemistry we have seen many a time. So iron can act as the metal for the porphyrin center or protoporphyrin 9 center in case of hemoglobin and myoglobin, for keeping all of us alive and can transport oxygen from lungs to different part of the body, and this is why our blood is also red, right. We have learned that and the intricacies of this chemistry. We have also learned the heme copper oxidases, once again the same iron chemistry but with a twist of adding copper into the mix. So you have the copper chemistry and the iron chemistry individually. In the last class we have summarized how the copper chemistry is, and today let us say in this part we will see how iron and copper can come to a compromise situation and can do wonder for the biological system. For instance, the cytochrome C oxidase, which is nothing but heme copper oxidase, it can convert oxygen into water. A very difficult transformation. If you look at it, requires 4 electron 4 proton overall to convert it into water. By doing so, it is participating in the proton gradient creation, and overall this is a very important transformation in nature. Okay. Cytochrome C oxidase has quite a few active species or quite a few metal centers that is involved. Of course, there is a iron copper center which is the one we will briefly discuss. We will not discuss about the cytochrome C center, which is the heme center supported by the axial ligands such as cysteine and histidine on both the side, on one side histidine, another side cysteine. So this is just the electron transfer side. There is another dicopper center which is responsible for just the electron transfer. Overall, it is the hopping of electron from cytochrome C to copper center to the iron center and all the way to the heme copper oxidase center. This is where the oxygen is taken up to be converted into the water. These are all membrane bound protein, as you have seen from the membrane here. Okay. So the active site in that heme copper oxidase or cytochrome C oxidase, main active site, of course there are other metal as you have seen, is this porphyrin iron center as well as this copper center. This is similar to what you have seen, let us say for one of the copper center of hemocyanin or tyrosinase, 3 histidine is there, but of course in hemocyanin tyrosinase you have 2 copper centers. Here 1 copper center with 3 histidine, but with a twist of adding this phenol, the tyrosine histidine cross-link phenol being appended right over there. This is the heme center where you have the iron center, and from the axial side there is this histidine. So proximal side is histidine and the distal side is open for oxygen coordination. Some crystal structure are there which is suggestive of some intermediate, but these are highly questionable. In any case, the proposed mechanism is such that iron will first form the iron superoxide species, just like what we were discussing earlier, just like you have seen in case of the hemoglobin, myoglobin, with the histidine coordination, it will bind with the oxygen to give the iron 3 superoxo. Iron would have been outside the plane, now pulled in with the histidine also moved in. Any case, this is going to be the iron 3 superoxo species, the very first form intermediate. Characterization of such intermediate in the synthetic studies is done, but most importantly it will immediately, almost immediately react with copper 1 to give rise to a peroxo intermediate. This peroxo intermediate could be the iron 3OO copper 2, or it could be a iron 3 hydroperoxo intermediate. All of these species will add up in reducing oxygen by multiple electrons, overall forming the water. Upon oxygen cleavage in this peroxo species, we would get the copper 2 hydroxo species in presence of this phenoxy radical formation via the hydrogen atom abstraction through this species. We would also get high valent iron oxo intermediate formation. We have seen the nature of these iron copper species. It could be an end on bound geometry, it could be side on end on bound geometry, or it could be side on and side on bound geometry. But most likely if it is a tetradentate ligand, then this is the species forming. If it is a tridentate ligand, this is the species is forming. Perhaps one can rule out such sort of species formation. Since we in the enzyme have a tridentate ligand, so this is the species likely to be forming in the enzyme. We have seen the crystal structure in synthetic setup for such intermediate, where iron 3 is having a side on geometry and end on geometry for the copper case. Finally, we were able to see that in synthetic studies both these side on bound as well as the side on end on and side on bound geometry can be interrogated further by a proton and electron to give the oxygen cleavage, which is nothing but forming water, because the protonation of these intermediates should give rise to the water formation. This is fantastic. We have seen in the summary for these synthetic model studies that these species is characteristic of each of these species are very characteristic. They have now very fingerprint like identification in terms of the UV visible spectra, resonance Raman spectra, X-ups, different other fast spectroscopic and sensitive spectroscopic technique can be utilized for characterizing the so formed intermediate. So the synthetic understanding is so far such that we can follow each and every step of what is happening in case of oxygen. So we can start with oxygen, reduce it by 1 electron to give the superoxo, another electron transfer to give the peroxo species, most likely this is the peroxo species formation, and then the protonation and further electron transformation, electron transfer cleaves the oxygen bond. Well, to summarize the synthetic efforts, what has been done so far is iron copper peroxo species has been characterized and synthesized and characterized, and upon adding hydrogen atom in the form of proton and electron, it was possible to detect this iron oxo species formation, which is definitely indicating that oxygen bond of oxygen dioxygen molecule is cleaved to form this species. Right. One can also independently start from these iron 3 peroxo species, where oxygen is reduced twice, one electron from iron, another from outside as a electron source to give the iron 3 peroxo species. These iron 3 peroxo species then can react with a equivalent of copper 1 as well as proton and base. This can give rise to this species. Just to remind you, if the base is not there, which is this one, this dicyclohexyl imidazole, this reaction does not work. Of course, if proton is missing, this reaction does not work. If copper 1 is missing, once again this has no relevance in terms of the iron copper heme peroxidase chemistry, right. So one can again reach out from a different angle also by synthesizing the axially ligated iron 3 superoxide species. One can then also interrogate such species towards the 2 equivalent of copper AN, where 1 equivalent will act as a electron transfer reagent to make it the iron 3 peroxide, another equivalent will react with it to further take you to the formation of this oxo species. So, to summarize the heme copper oxidases, of course you have seen the stepwise formation and stepwise understanding in the slides when we were discussing originally, but here to simply summarize that we understand that enzymes such as hemoglobin and myoglobin can reversibly bind oxygen, does not do any other oxygenation chemistry or any other advantageous chemistry, but in case of heme copper oxidases, as you have seen, this is quite fascinating, where oxygen itself is converted to water, but by taking advantage of both the heme iron center and copper chemistry together. So, it is combining the best of the two worlds of one of iron chemistry, another of copper chemistry, putting them together, such a very difficult transformation such as oxygen to water molecule conversion can be possible, and we have seen that this has a real implication in terms of our biological transformations. Okay. Now, moving the gear in summarizing this, so we will see the cytochrome P450, right. This rings the bell, right. We have discussed this cytochrome P450. Once again, this is a heme enzyme. Of course, here no copper is involved, just the heme center, but not here oxygen is going to be converted to water. Oxygen will be utilized to do the oxygenase chemistry. That means if you have aliphatic substrate, if you have many other substrate, the cytochrome P450 can do the reaction on the organic substrate. Cytochrome P450 is the best synthetic organic chemist ever. Almost the reactions the synthetic chemist cannot perhaps dream of doing efficiently can be done relentlessly smoothly by cytochrome P450, right. Cytochrome P450 is crystal structure. This is the camphor bound crystal structure. This is the heme side, but one notable change here from the previous cases of hemoglobin, myoglobin and cytochrome C oxidase is this cysteine thiolate binding, right. Cysteine thiolate binding is different. Previously it was the histidine coordination. Now this binding can be extremely efficient or extremely important both for the oxygen bond cleavage as well as your important iron high valent oxo intermediate stabilization, right. So these iron high valent oxo intermediate upon stabilizing, of course upon forming and little bit stabilizing, it can abstract hydrogen atom from the substrate and subsequently it can hydroxylate the aliphatic substrate, right. So the reaction mechanism, to sum very quickly, we have seen the iron 3 species which would be outside the plane, although this drawing does not reflect. This is the resting state of the enzyme. Organic substrate orient itself in front of the active site, oxygen binding as well as activation leads to superoxo, another electron transfer through this iron 4 cluster and the big chain of event that gives rise to the iron 3 peroxide species formation. Protonation gives rise to the iron 3 hydroperoxide species formation. Remember, none of these species formation are happening in case of the hemoglobin and myoglobin, but in case of cytochrome C oxidase, just like cytochrome P450, cytochrome C oxidase may have some similarity in these steps. We have similar perhaps intermediate in cytochrome C oxidase also, but none of these intermediates are fully characterized in those cytochrome C oxidases cases, but here we have informations that these species are called these compound 0 or iron 3 hydroperoxide species, which can undergo the cleavage of the OH bond to give the iron 4 oxo radical cation. So essentially iron 5 oxo, which can abstract hydrogen atom from RH to give the iron 4 hydroxo. Well, you have seen also the catalase activity and the peroxidase activity. If this pathway is not forming or this is not the desired pathway, oxygen is missing, or the electron transfer is not sufficient in presence of the hydrogen peroxide as an intermediate or as an active species, we can utilize these iron 3 species to settle between these iron 3 and iron 3 hydroperoxide. This is known as peroxide shunt, but this is the mechanism you have seen for the peroxidases, right. So, the peroxidase chemistry essentially involve the formation of these iron 3 hydroperoxide species starting from the iron 3 aqua complex. Directly from there it forms this intermediate, and from there on it can go on to give rise to the water molecule, right. And in presence of still it would require 2 H dot from the substrate, but overall it can give you from hydrogen peroxide to 2 equivalent of water, for alkyl hydroperoxide to 1 equivalent of alcohol and 1 equivalent of water. Of course, there is formation of these high valent iron oxide intermediate which can then further in presence of an electron and proton like H dot can give rise to this intermediate and then finally back to that intermediate. So, this catalytic cycle is also true for the peroxidase, right, that we have seen, and for the catalase we have seen that it is just the settling between these iron 3 intermediate and iron 4 oxoradical intermediate. These two intermediate settles here, just the H2O2 is taking part, and H2O2 is converted to 1 equivalent of water and 1 equivalent of oxygen. If enough H2O2 is not present, then the formation of this intermediate can be questioned or can be possible, but in presence of the reductants such as NADPH or so, even if enough H2O2 is not present, still these intermediate remain valid. No other intermediate is possible in those cases as well, right. So, this is quite interesting, they are quite interlinked, as you can see. Both the cytochrome C oxidase, cytochrome P450, catalase, peroxidase, all are playing very simple game of high valent iron oxo species formation, right. So, we have seen in cytochrome C oxidase, we are seeing in cytochrome P450, we have seen in the catalase, we have seen in the peroxidase. All of them are essentially forming high valent iron oxo intermediates, right, in different form. Now, as you have seen in case of cytochrome C oxidase, there is a iron copper center, these are only heme centered. Okay. The same diagram we have seen one more time in the form of the iron being outside the plane, how iron is pushed in, overall giving rise to this sort of intermediate, which is quite fascinating overall to follow, that this oxygen then react as well to give you the steps that we have just discussed. So, this is the same intermediate we have discussed, right. So far you have to study a little bit because otherwise it gets complicated or confusing, because these are related and these are similar yet distinct. They are not similar or same. They are similar but not the same. There are subtle differences you need to understand. So, the peroxidase chemistry, catalase chemistry and cytochrome P450 chemistry is very similar. You should read it together, understand the difference, and cytochrome C oxidase is little different. Of course, you have seen hemoglobin, myoglobin is completely different. They are kind of the no hassle enzyme. It just does one activity, and that is oxygen transport, right. So, that is quite interesting for all of us to remember. Moving on, what we have understood also clearly is this hemoglobin and myoglobin utilizes histidine, and cytochrome P450 type of enzyme utilizes this cysteine thiolate. Wherever the high valent iron oxo species formation and their stabilization is required, this cysteine intermediate is called upon. Nature has utilized heme center both for the reversible oxygen binding and oxygen activation and subsequent reaction. By changing the nature of the axial ligand from histidine to this cysteine, we have seen that nature tunes its reactivity, Protein side chain of course plays a key role. This sort of cysteine thiolate bridging helps you in overall hydrogen bonding, or the proton conduit to form the hydroperoxide intermediate, and then the oxygen cleavage becomes easier because of this big push that is coming out from the thiolate. So, the thiolate is negatively charged ligand, effectively it pushes the electron from the thiolate to the iron to all the way to the OO, and therefore the oxygen cleavage becomes easier. Overall, I would also say that these iron's high valent oxo species, once it is formed, that is this high valent iron 4 oxyradical cation, that is iron 5 essentially, can also be stabilized quite nicely by this thiolate cross linking or thiolate linkage. So, therefore, it is essential to understand the nature motive of making these almost similar thing, but really distinct thing by subtle changes. Nature did not play too much with these species, right. Alright, so that is about the heme chemistry. Let us say next look at the non-heme chemistry. Non-heme chemistry, as you have seen, are yet another avenue, right. This is once again very fascinating, right. So far we have seen at least one porphyrin is there. We have seen hemoglobin, myoglobin, cytochrome C oxidase, cytochrome P450, catalase, peroxidase, all of these cases we have at least one heme center. Now we want to get rid of the heme center and we want to put the simple ligand such as histidine, right. So, we have already seen in one case of just histidine, that is, but this is an unsymmetrical case, as you know, 3 histidine, 2 histidine, but this is the hemerythrin case which is not doing any sensitive chemistry, I would say, in terms of the substrate oxygenation or oxidation type of chemistry, but this is a pretty important reaction that it binds with iron center. Upon binding also it ends up transferring electron, that as we have summarized earlier, and this oxygen is really binding is really reversible. So, whenever it is required from this species, it can remove the oxygen and comes back to this species, right. So, this is important for marine vertebrates for their life, but there is no organic substrate to be functionalized in these cases, and these are well knit, well built intermediate. You see 2 iron center bridged by glutamate and aspartate and hydroxo, and this histidine ligand, unsymmetrical ligand, these are beautiful, right. But we do not we have seen earlier the spectroscopic features and everything, but let us look at some of the chemistry that can be done by these non-heme iron center. Of course, not exactly these center, but these are non-heme, right, because the porphyrin ring is not there. So, these are non-heme center. If you look at further, let us look at some of the hydroxylation chemistry that we have seen some time back. So, this hydroxylation chemistry is super important from the synthetic perspective as well. Of course, from the enzyme perspective it is very important, but it is also very exciting from the synthetic perspective. This mechanistic understanding goes as simple that for the synthetic studies as well, this iron 3 hydroxo is forming, it can react with hydrogen peroxide to give you the iron 3 hydroperoxo species. These iron 3 hydroperoxo species, these are all synthetic studies I am talking at this point right now. These iron 3 hydroperoxo species can undergo oxygen bond cleavage to form iron 5 oxohydroxo intermediate, right. Iron 5 oxohydroxo intermediate is formed. This iron 5 oxohydroxo intermediate is a super reactive intermediate, can abstract hydrogen atom from RH to give you R dot and iron 4 dihydroxy intermediate. This rebound between R dot and OH would give rise to the ROH intermediate, right. So, this is quite phenomenal. You have seen such sorts of high valent iron oxo species formation in case of cytochrome P450. Just a moment ago we were discussing cytochrome P450 also has essentially iron 5 oxo, which is iron 4 oxo radical cation, which can do quite a beautiful lot of chemistry with the porphyrin ring, but these are non-porphyrin ring or non-heme ligand system which are also capable of doing this chemistry, right. So, these are similar chemistry what we have seen in cytochrome P450, but these are non-heme iron chemistry, which is also quite exciting chemistry that we know of, right. Now, this cleavage of the oxygen-oxygen bond in iron 3 hydroperoxo can be influenced by water or by the carboxylic acid. Water can assist in this ring formation mode where the oxygen-oxygen bond cleavage becomes feasible and can form really iron oxo hydroxo intermediate, which can then undergo the epoxy and or the cis dihydroxylation product formation. In case of these hydroperoxo species, as you know so far, that these hydroperoxo intermediate can also undergo oxygen-oxygen cleavage with the help of the hydrogen bonding from, let us say, acetic acid. This acetic acid hydrogen bonding weakens or makes it easier to break the oxygen-oxygen bond to make the iron 5 oxo along with the carboxylate linkage. This carboxylate linkage linked iron 5 oxo once again can react with the olefin to give the epoxidation product. There could be quite interesting beautiful chemistry coming out of these as well. So, these are synthetic chemistry, but most importantly this sort of synthetic chemistry can be utilized in predictably selective hydroxylation chemistry, right. We can have predictably selective chemistry originating from these non-heme iron synthetic compound. We have this reactivity of these iron oxo hydroxo or high valent iron oxo intermediates are quite predictable in this nature, where tertiary is found to be more reactive than secondary than the primary center, right. If you can actually reverse this reactivity mode with the suitable electron withdrawing group. Once you have an electron withdrawing group present, that molecule becomes less reactive. In this case no electron withdrawing group is there, therefore it is more reactive. This tertiary center is very less reactive since electron withdrawing group is there. In this case this tertiary center is very close to an electron withdrawing group, therefore this is not that reactive as well. In fact, in such a case maybe tertiary is not reactive too much compared to even the secondary one. So, this sort of selectivity in case of olefin epoxidation can also be extended both in terms of the directing group, sterically demanding group, and as well as the electron richness can be monitored and can be predicted for a given organic substrate. So, depending on the substrate complex the substrate is, prediction for the hydroxylation site becomes much more easier, right. We have seen that, for example, if you are looking at this compound, well, you have a primary center, you have a secondary center, tertiary center, secondary center, of course primary center, but primary are not reactive, secondaries are not reactive too much, tertiary is going to react, and that is what you see. If you introduce a steric bulk, so this becomes not so prominent at this point because it is sterically, hydroxylation is sterically hindered, and therefore even the secondary center is getting reacted over here. Of course, if you have a secondary site or primary site, the product will be ketone, not the hydroxo product, because upon first hydroxylation further oxidation becomes inevitable and very facile the end up giving this product. Now, this sort of intermediate we have seen, this is the site of the reaction because these sites are deactivated by this electron withdrawing ester group. You can override this sort of bias of electron steric bias if you have a directing group. Instead of making it ester, if you make acid, then this acid is now going to direct this CH bond to give the corresponding hydroxylated product. That is fascinating. In this molecule, as you can see, you have one tertiary center, another tertiary center, another tertiary center. These centers is sterically encountered or hindered. This is also not too reactive due to the electron deficiency, and this is the site where the reaction is happening, and selectively this is the site where reaction is happening. It is important to also note that there are going to be other product, there is other product formation, but those are not too much compared to the major product formation. So, we can perhaps put those in on the side, but nonetheless they are forming, right. So, more the complex substrate you have, better it is for its predictably selective functionalization. In this case, out of all different CH bond that is present in here, selectively this hydroxylation can be possible. In this case, even the keto formation becomes difficult because of the steric hindrance. So, this is a highly engineered substrate, highly complex substrate, and the prediction becomes much more easier. So, in this type of chemistry, just let me conclude by saying that the value of this aliphatic CH hydroxylation or CH oxidation reaction for late stage synthesis rests on how predictive the electronic, steric and carboxylate directing modes of selectivity are in complex molecular setting. In other words, more complex the substrate is, better it is for the active species to do the chemistry selectively. With this, we will come back again. Thank you very much.